Good evening to all. Okay, today I'll continue with a topic, moment of inertia. Okay, it is a complex topic of engineering mechanics, so I think that it is good to give a PPT on this or a video on this. Okay, so continue with the topic, moment of inertia and its physical significance. Okay, so what is moment of inertia? First of all, we need to know. Moment of inertia is what? What is moment? Okay, moment is nothing. When I'm talking about moment, little rotation strike on your mind. Okay, so moment of inertia. Inertia is what? Whenever I applied a force on any body, the body will resist that force. After the resistance, it will move. Okay, so whatever resistance provided by a body, it is due to inertia. So what is moment of inertia? Whenever a body provided a resistance about angular rotation, so at that time you can say that it is a moment of inertia, right? So in our words, the moment of inertia of rigid body about a fixed axis is defined as the sum of product of masses of the particles constituting the body, the square of their respective distances from the axis of rotation. Whenever I come to the definition, the previous one is this, okay? Whenever I'll come to the formula, at that time you need to follow this equation, this definition. So according to this definition, I can say that mass moment of inertia is nothing. It is mr square, okay? According to this definition, it is a product of mass and square of radius, okay? So this radius is what? Radius of gyration. So according to this definition, I can say that I is nothing, it is mr square. Whenever I'm talking about number of particles, like maybe there is some particle, a number of particles are in a body. At that time, that particular particle, if m1 is a particular particle and the distance of m1 from the CG is r1, okay, at that time I can say that the mass moment of inertia of that particular m1 is m1 r1 square. Okay, whenever I'll come to another particle, that is m2, so it is m2 r2 square. I'll come to third particle, it is m3 r3 square. And whenever I'm talking about the total body, at that time I can say that I is nothing, it is summation of m1 r1 square plus m2 r2 square plus m3 r3 square, or number of particles like m and rn square. Okay, the dimension of this mass moment of inertia is ml square. How can we find this? Mass dimension is kg and unit is kg and radius unit is meter square. So I can say that the unit of this overall is kg, mr is m square, kg meter square. So in kg meter square is converted into ml square in dimension form. Come to next slide. In this slide, we can understand that what is the use of mass moment of inertia, or you can say that how can we understand in simple words the moment of inertia. The mass moment of mass of body resists a change in its state of linear motion. If a body in linear motion, at that time a resistance provided on that body, it is a inertia provided on that body. Okay, whenever the moment of inertia of body about an axis of rotation resists a change in rotational motion. Okay, the greater moment of inertia of a body, the greater is the torque required to change the state of rotation. Whenever I'm talking about rotation, at the term of force, I can take torque. Okay, because torque is a force that is provided for rotation. Okay, this moment of inertia of body can be regarded as measure of rotational inertia of body. The moment of inertia of body plays the same role in the rotational motion. As in linear motion, the inertia plays a role, same as in rotational motion, the moment of inertia plays a role. That is why moment of inertia is called rotational analogous of mass in linear motion. Okay, that was the definition of mass moment of inertia. I always whenever I talking about moment of inertia, I take a word mass moment of inertia. So mass moment of inertia is I is equal to mr square. Actually, moment of inertia, and we can define the moment of inertia in two terms. One is mass moment of inertia, another is area moment of inertia. So in our next lecture, we will discuss about area moment of inertia. The mass moment of inertia is tougher than area moment of inertia. That's why I'll take this first and then we take another part of this. Okay. So when I'm talking about rotational movement, at that time, rotational acceleration, I want to know the torque. Okay, you have to know the torque. Torque is what? Actually, the people are confused in this word. We properly knows that what is force. Okay, whenever I'm talking about torque, the people are confused. Actually, it is nothing. As I'm talking about, whenever I'm taking any body in a anybody apply a force on this particular lever. If it is attached, like it is attached on a O point, and a force is applied vertically on this rod, so I can see that if it is rotated about O, it will turn like this. Okay, if it will make a circle. Okay, at that time I can say that the force causes, if it is a linear motion, the force causes acceleration. Whenever it is angular motion, I can say that it is an angular acceleration it will give. So the force is converted into torque. So I think you are able to understand what is torque. Let be a force acting on an object, that is like R is the distance of this particular, the distance from O is R. A force is applied on this vertically. Okay, so magnitude of torque at that place, I can say that F into R. As we read about moment is nothing. It is what? Force into perpendicular distance. Same as the force into perpendicular distance is movement. Okay, so this is also movement. So tau is equal to R into F, distance multiplied by force. Okay, if I want to find the dimension of torque, I can see that it is Newton meter easily, because force giving the dimension is Newton and R giving a unit meter. So I can say that the torque is having a unit of Newton meter. Come into radius of gyration. This is also an important term that is used in moment of inertia. Okay, whenever I say that I is equal to mr square, right? So mr square, R is radius. What radius? It is not a simple radius. If a mass is m1 in this body and R is the distance, one a reference axis, that is AB. AB is a reference axis. Okay, whenever I want to find any distances with respect to x, with respect to AB, I can see that radius are radius of gyration. Okay, so radius of gyration is nothing for any body capable of rotation about given axis. Okay, given axis, that is AB. About given axis, it is possible to find a radial distance from the axis, where if whole mass of the body is concentrated, its moment of inertia will remain unchanged. Whole mass is concentrated, like the total mass is acting on a particular point, that is concentrated. Its moment of inertia will remain unchanged. The radial distance is called radius of gyration, like m1 radial distance is r1, m2 radial distance is r2, m3 radial distance is r3. Okay, the radius of gyration of body about its axis of rotation may be defined as the distance from the axis of rotation at which, if the whole mass of body were concentrated, its moment of inertia about given axis would be same as actual. Okay, say if I want to formalize that radius of gyration, I can easily say that I is nothing. I is in terms of, I can write that k square. K is what? Radius of gyration. K is denoted for radius of gyration, and I can easily write I is equal to mk square. How can I say that? I know that I is equal to mr1 square plus mr2 square plus mr3. Number of, like in previous slide I read about moment, this formula I is equal to m1 r1 square m2 r2 square. Okay, the same formula used here, like m r1 square plus m2 r2 square. The mass is similar, that's why m used everywhere. So mass take common of m. then R1, R2, R3 are in the summation of that radial dimension distances. So R1, R2, R3, these are number of distances. So I can write as n number of distances are there. So n multiplied by at top and bottom, then m into n, this is written like third line. Now I is equal to, if number of particles of m masses, I can write that m into n is nothing. It is capital M, total mass. Okay, the total mass in bracket, these all radial distances divided by n. So this whole formula is converted into I is equal to mk square. If k is nothing, it is this constant is converted into k. So from here I can find the formula of k. K is what? Radius of gyration. The k I can write as I is equal to mk square. Mk square is equal to m, so m cancel on both sides. The k value is under root r1 square plus r2 square plus r3. This is the formula of radius of gyration. So I can say that in another time I can define the moment radius of gyration, that is radius of gyration of body about an axis of rotation may also be defined as the root mean square distances of particle from the axis of rotation. Okay, factor on which radius of gyration of body depends, that is position and direction of axis of rotation. Axis of rotation, position, that is R1, R2, R3, position and direction, in like M1 is positioned on another side. So position and direction, sorry, distribution of mass about axis of rotation. Okay, how can we distribute the masses? Now, these are the basics of mass moment of inertia, that is the torque used to create mass movement, to create a moment of inertia. These are the significance of moment of inertia. Now we come to the another part of it. I can extend this topic now. In the extension of this topic, I know that there's two theorems are used for moment of inertia, which help to find the moment of inertia. That's why these theorems are used for moment of inertia. So we read about it in this. State and prove the theorem of perpendicular axis. These two theorems are perpendicular axis theorem. Another theorem is parallel axis theorem. Okay, one is perpendicular axis theorem. First we discuss about perpendicular axis theorem. So perpendicular axis theorem is nothing. The moment of inertia of plane lamina about an axis perpendicular to the plane is equal to the sum of moments of inertia of the lamina about any two mutually perpendicular axes, okay, on planes and intersecting each other at point where the perpendicular axis passes through the lamina. We know that x, y, z are perpendicular axis. There is 3D. If this body is 3D, so these three dimensions are there. One is x, another is y, the third one is z. If you want to understand this three dimension, you can easily see the corner of your roof, and we can see that one is vertical direction, another is horizontal direction, the third perpendicular direction is there. Okay, so these three perpendicular direction, a single point having three perpendicular direction if it is a 3D point. So x, y, z, these are the three dimensions. Now, if O is the origin of, or you can say CG of this particular body, and there is a point P situated on this particular body xy, which coordinate are xy. Okay, the xy coordinate shows that the horizontal distance of this point is x and vertical distance is y. Okay, in this we take the x distance is this, another y distance is this. Okay. Now, if I want to find that r, I can easily say that according to Pythagoras, r square is equal to x square plus y square. A simple mathematical formula. If I come to mass moment of inertia, the mass moment of inertia of a particle about x-axis. Listen, if I want to find the x-axis, this x-axis moment of inertia, at that time I have to take the distance y. You can see that from, you can see here, this distance. Okay, this is if I want to find the moment of inertia of IXX, okay, at that time I need to rotate the whole body about XX, okay. If I want to rotate the whole body about XX, so this Y is everywhere the radius, right? If this Y is everywhere the radius, I can say that I is nothing, it is my square for IXX, right? If I'm talking about IYY, okay, if I want to find the IYY, moment of inertia about YY, that means the whole body rotated about YY, okay. That's at that time the radial distance is X. So I can say that I is nothing, it is mx square, right? This is mx square, okay. Moment of inertia about x-axis is, say, summation of my square, and same as the iy is summation of mx square. Now, if I add the both moment of inertia ixx, iyy, because I want to find the total polar moment of inertia iz, at that time I need to add both. So when I started to add summation of mr square, okay, iz is nothing. See, when I want to find out the iz, I can simply say that it is rotated about r, okay, it is rotated about r. So I can write that iz is nothing, it is summation of mr square, and I know that r square is nothing, it is x square plus y square. So I put the value of x square plus y square in place of r, and summation of my square plus mx square is iz is equal to ix plus iy, okay. So this proves the theorem of perpendicular axis theorem. This is the perpendicular axis theorem. It is also called a polar moment of inertia. Whenever I want to find a polar moment of inertia, at that time I just added the moment of inertia about xx and about yy, okay. The next theorem is parallel axis theorem. The moment of inertia of a body about any axis equal to its moment of inertia about a parallel axis through its center of mass plus product of mass of body and square of perpendicular distances between two parallel axes. Understand this theorem? It is nothing. See, what it said, that simply if I want to find out the moment of inertia about any reference line, like PQ is a reference line, okay, I want to find out the moment of inertia about PQ. Okay, so it is nothing. It is simply the moment of inertia about CG, center, the moment of inertia about center point. Okay, the moment of inertia about center point plus IC plus the moment of inertia of body about moment of inertia about parallel axis center, and then add the term area multiplied by this particular distance. Okay, this term is added in moment of inertia about C. The parallel axis theorem is nothing. It is a summation of I moment of inertia about CG plus mass multiplied by distance of CG line to the reference line. Okay. If a body, if like it is a rectangular body, okay, if it is a rectangular body, at that time there is a CG axis, okay, centroidal axis. The distance from centroidal axis to the reference axis, wherever you want to find out the I, the distance between the centroidal axis and wherever you want to find out your moment of inertia, the distance between these two axes are square of this distance, md square. Okay, so I can write that md square. This is a parallel axis theorem. Actually, this is a parallel axis theorem. What is the use of this theorem? Whenever I want to find out moment of inertia of particular body with respect to any other axis, okay, like this is a body and their centroidal axis lies in particular body, like this is a body here, okay, there is example, if this is a rectangular, this is a centroidal axis, okay, but I don't need to find I don't need to find out the moment of inertia about centroidal axis. I need to find out the moment of inertia about this AB. Okay, if I want to find out the moment of inertia about AB, how can I find out this? Because I read the formula, to find the moment of inertia about centroidal axis, that is I is equal to mr square. Okay, but whenever I need to shift it on another axis, at that time I need to use the parallel axis theorem, that is the moment of inertia about centroidal. Okay, so moment of inertia about center is simply, for rectangular channel it is BD cube by 12. Okay, further you read it, ICG is BD cube by 12. Okay, plus, because this is the value of moment of inertia at center IC. Okay, if I want to find out the I, if I need to find out the I, at that time I is nothing, IC, whatever you find out it, BD cube by 12 plus mass of that particular rectangular channel, plus this is an example of in the terms of area. So you can use the area at that point. There's two type of body. One is subjected to mass or weight, and in some bodies we don't know the mass or weight. At that time we need to find and I need to find out the moment, the CG of that particular body. So to find the CG of that particular body without mass or weight, we find it with the help of area. So in place of mass, I can use the area also, and that particular moment of inertia is known as area moment of inertia. Okay, so this is a mass moment of inertia. So mass is placed on here, multiplied by distance. If this is something 2 meter and the distance 3 meter below this, we need to find out the moment of inertia. So the value of this d is 5. Value of this d is 5. Okay, so I can easily find out the moment of inertia about any axis. Centroidal axis we can easily find out with the formulas. If I need to find out the moment of inertia in any other axis, at that time you use the parallel axis theorem. Okay, whenever you need to find out the polar moment of inertia, you use the perpendicular axis theorem. Okay, this is the basic concept that is used for mass moment of inertia. The both theorem, that is parallel axis theorem and perpendicular axis theorem, both theorems are used in area moment of inertia also. Okay, so mass moment of inertia or moment of inertia or area moment of inertia, the concept of all is similar. Come to next, that is, now we need to know some particular, casually used diagram like circular plate, circular cylinder, rod. These are the normally used form in which we need to find out the mass moment. We need to find out the moment of inertia. These things are in terms of mass. That's why we use the mass moment of inertia for this type of diagram. Okay. Now, first of all, we started with circular disc. Okay, moment of inertia of circular disc about any axis through its center of and perpendicular to its plane. See, circular disc is what, like CD. You DVD player use a CD. That CD is a circular, a hole in between, but you don't consider it. This simple, a plate, like a plate. Okay, circular disc like a plate. As shown in figure, this is a circular disc. We need to find out the moment of inertia of that whole circular disc. To find the mass moment of inertia of whole body, we need to divide it in particular parts like M1, M2, M3 in the whole body mass. Okay, so here also we need to divide it in number of rings. Okay, when I cut a ring, when I cut a plate here, this is a ring. We can cut out a ring here. Okay, a ring is cut out from here. This ring, the area of this particular disc is easily, what is it? It is a circular plate. I can easily say that the area of disc is pi r square. Okay, when I need to find out the mass per unit area of disc, I simply say that mass per unit area. So pi r square is area, mass upon pi r square. This is mass upon, okay, this is pi r square. We can imagine the disk to be made up of large number of concentric rings. Number of rings are making a circular plate, okay, whose radius from O to like x2, x3, x4. Okay, so this is a circular ring that cut at x distance from O. Area of that particular ring is simply the circumference of this ring, okay, multiplied by its width. So circumference multiplied by its width, circumference is 2 pi r is circumference, but there is a distance. The radius of this particular ring is r now. So at that time I can say that this is in distance of x, so 2 pi x, okay. 2 pi x is circumference and multiplied by its thickness, that is dx. The mass of concentric ring, whenever I need to find out the mass moment of inertia, is 3 types of diagram are there, 1D, 2D, 3D, okay. Whenever I need to find out the mass moment of inertia, for 1D, I need to assume something like rho. Rho is something, okay. We know that rho is density. Density is nothing, it is mass divided by volume, okay. Density is the body density, like mass upon volume is density, okay. So mass upon volume is density, but it is used for 3D. We know that volume is used for 3D, okay. Whenever I talk about 2D diagrams, at that time I can say that, I can assume that actually rho is mass upon area, okay. And the circular plate is 2D diagram. This is a 2D diagram, okay. That's why I use the mass upon area, okay. Otherwise, I use the something, if it is a 3D diagram like cylinder, at that time I use mass upon volume, okay. 1D diagram like rod, at that time I can simply assume that for 1D, I easily assume that rho is nothing, it is m by L. See, mass upon volume. Volume is like x, y, z, okay. Now, mass upon area, because it is 2D, so one dimension is negligible. So, at that time, area into 1 is volume, okay. Here, the area into L, the area is 1. So, I can say that the m upon L, okay. So, this is a 2D diagram. That's why I use mass upon area, that is pi r square, okay. Mass of the concentric ring, I want to find out the mass of this particular ring, okay. How can I find out this? It is simply, if I assume that rho is equal to mass upon area, okay. I assume that rho is equal to mass upon area. I need to find out the dm. If I need to find out the dm, rho is equal to dm divided by area, okay. Area of that particular diagram, okay. I need to find out the dm, so I can say that rho A is dm, okay, rho A. So, this is rho and A is, right, this is smaller mass, dm is nothing, it is rho into A, rho, that is that we find out m by pi r square, and area, circumference multiplied by width we used here, okay. So, easily the dm, the mass of that particular ring is 2mx dx divided by r square, okay. If you are able to find out the dm, it is very easy to find out the moment of inertia. Now, I want to find out the moment of inertia, this particular ring, di is equal to m mass of the ring, and x, that particular radial distance ka square, the radial distance is x, so mx square, okay. Put the value of dm, this is dmx, so put the value of dm value is 2mx dx divided by r square, this one dm multiplied by x square, okay. So, di is nothing, it is 2mx cube dx by r square. Now, integrate this total, this di to find out the moment of inertia of that circular plate, okay. So, I is nothing, it is integration of di with in the reference of 0 to r, okay. So, integrate this particular value and put the value, put the r value in place of x, okay, and easily we get half mr square, that is the moment of inertia of circular plate, okay. Now, we will continue in our next lecture. Thank you so much.